In this video, we're continuing our discussion of the projection operator. The playlist for all the videos is at the website digital-university.org. Now, what we did in the previous two videos, we considered the projection of a vector B onto another vector A, and we derived a formula for a matrix that does that projection. It's this here. This, of course, is just the magnitude squared of the vector A that we're projecting onto, because we're just taking an inner product. But as we showed now in the previous videos, this is actually a matrix, a symmetric matrix at that. Now, what we're going to do in here in this video is the same type of phenomenon, only here we have a vector B and we have two independent vectors, A1 and A2. So by taking linear combinations of A1 and A2, they can actually form a plane. And we're asking ourselves, well, if we have a vector B that does not lie in this plane, is there a vector in the plane that is closest to vector B? That is there a particular vector in the plane so that this distance here is minimized? And of course there is, and which vector it is, we find that by realizing that this then, when it projected onto the plane, is orthogonal to it. So the vector closest to it is the one that starts at the origin and goes to that point of intersection at that, and they're orthogonal. Now this is orthogonal not only to vector P, of course, but to the entire plane. And this dotted line is really a vector. It's the vector B minus the vector P. So when we're finding the vector in the plane closest to B, what we're doing is we're finding B minus P that has the smallest value. And of course the vector that has the smallest value is the one that's perpendicular to the plane. So here we have two independent vectors, A1 and A2. Here we have a vector B, and now we're going to project vector B into the plane of A1 and A2, rather than projecting vector B just onto a single vector like we did in the previous videos. A1 and A2, of course, they each have an x1 and an x2 component, so we'll symbolize it like this. Same thing for A2. It has an x1 and an x2 component. Now, in our discussion here, what is key then is that we said B minus P is perpendicular to the plane. And of course, the plane is just linear combinations of vectors A1 and A2. So then that would mean that B minus P is perpendicular to the vector A1, and B minus P is perpendicular to the vector A2. Again, this is perpendicular to the entire plane, so of course it's perpendicular to vectors A1 and A2. Now, and remember, A1 has, we write like this, A2 we write like this. If this is perpendicular to A1, then that means that the dot product is 0. So we would have then vector A1 transpose times B minus P equals 0. Remember, when we're taking the dot product of two vectors, we always write our vectors as column vectors. When you take the dot product, then you have this as a row vector. So we write this as A1 transpose, as you saw us do in our previous videos. Then we also have from here A2 transpose times B minus P equals 0. Now, here's A1, here is A2, so let's make a matrix comprised of these two. So matrix A would be A1, X1, A1, X2, and then the second row would be, or second column would be A2, X1, A2, X2. Now, what we can do right here, though, is these would be the components of A transpose. What we have is more specifically is like this. A1, the vector A1 is this. Transpose is a row vector. It looks like this. A1, X1 plus A1, X2. That's just simply writing our column vector as a row vector. It's A1 transpose times B minus P equals 0. Then, likewise, for A2, we have A2 X1 plus A2 X2 times B minus P equals 0. Well, notice what this right here is. This is vector A transpose. Here we have A1 X1, A1 X2. Of course, if we take the transpose of this, we'll have A1 X1, A1 X2. That column becomes a row, because we did take A1 transpose. Same thing here. So we can write this as one equation, simply A transpose times B minus P equals 0. And remember, our vector A is comprised from A1 and A2, those two vectors. That is our matrix A. Now, P the projection vector, that lies in the plane, which means that P can be expressed as some linear combination of A1 and A2. Or, stated another way, we would say that vector P lies in the column space of vector A. We're saying then that there is some special vector so that A, we'll just call the special vector x tilde, that this equals P. Now, why do we write it like that? Remember, when we're multiplying matrices, this would be matrix A times vector X gives a vector B. Well, of course, remember how we multiply. We go across and down and add up to get that component. and keep going like that. Or the other way of thinking of multiplication, which we talked about back in video 7a, is that it's the same thing as the first component times the first column vector plus the second component times the second column vector plus the third component times the third column vector equals this. That also is a way to think of matrix multiplication, meaning that if we have an expression AX equals B, and there really is an X that satisfies that equation, what that means then is that vector B is some linear combination of these column vectors that is found in matrix A. Or another way of saying it is vector B is in the column space of matrix A. And that's exactly what's happening here. This is some linear combination of A1 and A2. And A1 and A2 are the columns of matrix A. So that means this is in the column space of matrix A. So if it's in the column space of matrix A, then there has to be some special vector X so that A times X equals that projection vector P. Now, let's substitute this for this. We have A transpose times B minus A X equals 0. What we want to do is find out what this special vector X is. Now let's look at here, just multiply across. We have A transpose B minus A transpose A times that special vector X equals 0. Now, we'll discuss this in more detail in a few moments, but what we want to say right now is that this vector, or this matrix, A transpose times A, we start with A being a square matrix. Even if A is not a square matrix, this will be a square matrix. It will be symmetric, and most of the times, we'll explain in a few moments, this will also have an inverse. This will be non-singular. We'll talk about that in just a few moments. What that means, though, is that, yes, this does have an inverse. So what we can say then is that the special vector X tilde equals A transpose, this is times vector B, A transpose B times A transpose A inverse. Putting this over here and then just multiplying through by the inverse gives us this expression. And again, we'll explain why, or more detail about why this is non-singular and so forth. But for now, just accept the fact that it is, and that gives us then how we can find that special vector X. Now remember, the projection P is A times that special vector. P, of course, was this, so that's going to be equal to P is A times this. So P is A times A transpose A inverse times A transpose times the vector B. So let's go back to where we began. We have a vector B. We have two linearly independent vectors, A1 and A2. They form a plane. We use them to make a matrix with these two out of their components. Then what we discovered is that this projection is equal to the vector B times this. And that is called the projection vector. Let's write it over here. So we have the projection vector P that equals A times A transpose A, that product, take its inverse, times A transpose. That is the projection vector P. When we are taking a vector B and putting it into a plane. Now, if we're dealing with a more complicated situation, we're not just projecting into a plane, but say a subspace, so that there's more than two linearly independent vectors. There might be 3, 4, or 5, or 6 of them. All that means then is that our matrix A is going to have more rows and more columns, but the formula is exactly the same. And this seems like sort of a cumbersome formula, but if you look back at what we did in the very first video, when we were projecting vector B just onto a single vector, we had this equation for the projection matrix. And we explained that this column vector times that row vector is a matrix, but this is just the inner product of the vector A with itself, so that's just the magnitude of it squared, so this is just a number. But here, we're dealing with matrices. A transpose A is not a number, it's another matrix. It does have an inverse, as we'll explain, but we still have A times A transpose, only these are matrices now. Here these were vectors, and then instead of having this with the matrix, we have this with an inverse. So this is very much analogous to what you saw us do in the previous videos when we were just dealing with projecting onto a single vector. So this then is our general formula here for a projection matrix when we have a vector and we're projecting it into some subspace. That subspace might be spanned just by 2 linearly independent vectors, or maybe 3, 4, 5, or 6. All that means is that our matrix A will have more rows and columns than what we have right here, but the formula is exactly the same. Now, let's talk about A transpose times A. Sometimes that's called a normal matrix. And let's say that we're not dealing just with square matrices, but let's say that matrix A is a non-square matrix. Maybe matrix A is m by n. Well, A transpose, that will be n by m. We multiply the two together to get a single matrix. That will be a square matrix, n by n, and we can see this is also a symmetric matrix. If we take the transpose of this, How do we do that? We take transposes and we also reverse the order of multiplication. So this belongs on the left with the transpose. This belongs on the right with the transpose. But A transpose transpose is just A. So this is a symmetrical matrix. It's equal to its transpose. And if we have here then m by n, so we're not dealing with a square matrix anymore. When we multiply, we do get a square matrix. Furthermore, and we'll prove this in one of the future videos, if all of these columns of A, all n of them, are linearly independent, then this is non-singular. It has an inverse, provided all the columns that exist in vector A are linearly independent columns. And why that's true, we'll prove that in a future video. Okay, that's it for this video. In the next two videos, we'll work some examples here using the projection operator. And once we do that, then we'll explain why it's so important to be able to use the projection operator and how that applies to least squares problems.